Our universe is filled with cosmic contradictions. For every law of physics we think we have pinned down, the cosmos reveals a piece of evidence that simply does not fit. This video is a journey through 25 of those baffling discoveries, each one a crack in the foundation of our current scientific understanding. By the end, you will see the night sky not as a static map, but as a living puzzle box of unsolved mysteries. We will encounter signals from the void that defy explanation and forces that control the fate of everything yet remain completely invisible. What single cosmic mystery do you find most unsettling? The first and perhaps most profound crack in our cosmic understanding is a ghost. Picture a galaxy, a magnificent spiral of billions of stars swirling gracefully through the void. According to the laws of gravity, stars on the outer edges of this spiral should orbit much slower than those near the dense, bright center. It is a simple principle, like a child on a merry-go-round. The further you are from the center, the slower you spin. But when astronomers measured the actual speeds of stars in these galaxies, they found something impossible. The outer stars were racing around just as fast as the inner ones. The entire galaxy was rotating as if it were a solid disk, not a collection of independent objects. The visible matter, all those stars and glowing gas clouds, simply did not have enough gravitational pull to hold these speeding stars in place. The galaxy should have flown apart long ago. Something invisible, something that does not emit or reflect any light, was providing the extra gravity. We call this phantom substance dark matter. The evidence does not stop there. When we look at immense clusters of galaxies, we see them bending the light from more distant objects behind them, a phenomenon called gravitational lensing. The amount of bending is far too severe to be caused by the galaxies we can see. It is as if each cluster is wrapped in a massive, invisible cloak of gravity, warping the fabric of space itself. This dark matter forms a vast, intricate scaffold across the cosmos, a cosmic web upon which the luminous galaxies are merely the glittering decorations. And here lies the staggering mystery. This invisible stuff is not a minor component. It makes up roughly 85% of all the matter in the universe. Everything you see, every planet, every star, every person, is just the visible froth on an ocean of something we cannot touch, see, or directly detect. For decades, scientists have built exquisitely sensitive experiments deep underground, hoping to catch a single, fleeting interaction of a dark matter particle. So far, the detectors remain silent. We are surrounded by the architecture of the universe, built from a material whose true nature remains utterly unknown to us. If dark matter is the invisible scaffolding holding the cosmos together, then the second discovery is the force actively trying to tear it all apart. For most of the 20th century, astronomers knew the universe was expanding, a consequence of the Big Bang. It was a reasonable assumption that this expansion was gradually slowing down over time, as the collective gravity of all the matter in the universe pulled back on the fabric of space, acting like a cosmic brake. The only real question was whether the universe had enough matter to eventually halt the expansion entirely, leading to a big crunch, or if it would simply coast onward forever, growing ever larger but at a steadily decreasing pace. Then, in 1998, two independent teams of researchers made a measurement that shattered this entire picture. They were studying a specific type of stellar explosion, a supernova that acts as a standard candle, a cosmic yardstick of known brightness. By observing these supernovae in galaxies incredibly far away, they were looking billions of years into the past, measuring how fast the universe was expanding at different epochs. The data revealed something impossible. The most distant, ancient supernovae were dimmer than they should have been. This meant they were farther away than our models predicted. The expansion of the universe was not slowing down. It was speeding up, some mysterious repulsive force acting against the pull of gravity was pushing galaxies apart at an ever-increasing rate. We named this force dark energy. The implications are staggering. Dark energy is not just a minor player, it dominates the entire energy budget of the cosmos. While dark matter makes up about 27% of the universe and all normal matter a mere 5%, dark energy constitutes a colossal 68%. It is the primary component of reality woven into the empty space between galaxies, yet we have no idea what it truly is. The leading candidate is a property of space itself, a constant energy density that causes a repulsive gravity as the universe expands. But its origin and precise nature remain one of the greatest enigmas in physics. This discovery rewrote the ultimate fate of everything. Instead of a big crunch or a gentle coasting, the current forecast is a cold, lonely, and relentless expansion. Over trillions of years, galaxies outside our local group will be pushed away until they vanish over the cosmic horizon, their light never able to reach us again. The universe will become a vast, dark, and increasingly empty void. We live in a cosmos ruled by two profound mysteries: dark matter holding structures together and dark energy ripping them apart, locked in a battle that will determine the destiny of all existence. Gravity's hidden hand does not stop at the edges of our galaxy. Our entire Milky Way, along with its neighboring galaxies, is caught in a vast, silent river, all flowing toward a single point in the cosmic darkness. This is the mystery of the Great Attractor. Astronomers first noticed this strange drift decades ago when mapping the motions of galaxies across our local universe. Everything, including us, is moving at over 600 kilometers per second toward a region of space near the constellation Norma. It is as if a colossal, unseen mass is reeling us in. The problem is, when we look in that direction, we do not see anything massive enough to explain such a powerful gravitational pull. The visible galaxies there, like the Norma cluster, are significant, but they are simply not heavy enough to be the sole cause. To make the mystery deeper, the precise location of this gravitational epicenter lies directly behind the plane of our own Milky Way galaxy. This area is called the zone of avoidance. It is a crowded, dusty shroud of stars, gas, and cosmic debris that completely obscures our optical view, like trying to peer through a dense fog bank. For a long time, this zone was a blind spot in our maps of the universe. Modern astronomy, using X-ray and radio telescopes that can pierce through the galactic dust, has begun to lift the veil. What they have found is not one simple answer, but a more complex truth. The pull we feel appears to be caused by a staggering concentration of mass known as the Laniakea supercluster, a cosmic filament of hundreds of thousands of galaxies, of which our own Milky Way is merely a suburban outpost. The Great Attractor seems to be the gravitational center of this immense structure. Yet, even this discovery does not fully resolve the puzzle. The sheer amount of gravitational force suggests there must be far more mass there than the visible galaxies account for, pointing once again to the pervasive influence of dark matter woven into the supercluster's fabric. So we are left with a cosmic tide pulling us toward a hidden heart of darkness we are only beginning to map. A reminder that even the motion of our entire galaxy is dictated by forces we cannot yet see. The pull of unseen giants is not the only signal from the void that defies explanation. On a quiet Ohio night in August 1977, a radio telescope known as the Big Ear was performing a routine survey of the sky. It was listening to the cosmic static, the faint hiss of natural radio waves emitted by stars and gas clouds. Then, for exactly 72 seconds, the silence was shattered. The telescope's computer printout recorded a signal so powerful and so strange that a volunteer astronomer, Jerry Amon, famously circled the alphanumeric code on the printout and wrote one word in the margin. Wow. The wow signal, as it became known, was everything scientists had theorized a deliberate extraterrestrial transmission might be. It was a strong, narrowband radio burst focused on one specific frequency, the hydrogen line, which is a quiet channel in the natural radio spectrum and a logical place for a cosmic civilization to send a beacon. It rose to peak intensity and then faded away as the telescope's fixed gaze moved with the rotation of the Earth, exactly the pattern expected for a signal from a distant point in space. And then it was gone. Despite decades of repeated and targeted searches, the signal never returned. The hunt for a natural explanation has been equally frustrating. It could not have been a passing satellite or aircraft, as those use broad, sweeping frequencies, not a single, pure tone. A recent hypothesis suggested it might have been radio emissions from a hydrogen cloud surrounding a comet, but the comets known to be in that region of the sky at that time were nowhere near the telescope's field of view. So we are left with a singular event, a perfect cosmic shout that lasted just over 1 minute and has never been heard again. It stands alone in the history of SETI, the search for extraterrestrial intelligence, as the best candidate we have ever found. A signal that passed every initial test for artificial origin, emerging from the constellation Sagittarius and then vanishing back into the silence from which it came. Was it a fleeting malfunction of some human technology, a bizarre and unrepeatable natural phenomenon we still do not understand? Or was it a momentary glimpse of a distant intelligence, a message sent across the light years that we heard for just 72 seconds and then lost forever? The WOW signal offers no answers, only a profound and enduring question hanging in the static of the cosmos. The profound silence following the WOW signal leads us to a deeper, more unsettling cosmic contradiction. Enrico Fermi, a physicist, famously posed a simple question over lunch one day. If the universe is so vast and so old, with billions of planets that could support life, then where is everybody? This is the Fermi paradox. The math seems overwhelmingly in favor of alien existence. Take the Drake equation, a formula that estimates the number of communicative civilizations in our galaxy. Even using conservative numbers for factors like the fraction of stars with planets or planets that develop life, the result suggests there should be many civilizations out there. Some should have arisen millions or even billions of years before us, granting them more than enough time to spread across the galaxy, building structures we could detect or sending signals we could not miss. Yet our telescopes hear nothing but natural static, and our sky shows no clear signs of engineering on a cosmic scale. This deafening silence is itself a discovery, a data point of profound emptiness. To explain this great quiet, scientists have proposed many unsettling solutions. One is the Great Filter. This idea suggests that somewhere between the chemistry of a lifeless planet and a galaxy-spanning civilization, there is an evolutionary or technological step so difficult, so lethal, that almost every species fails to pass it. It could be that the leap from simple single-celled life to complex multicellular organisms is astronomically rare, or more chillingly, the filter might lie ahead of us in our future. Perhaps every advanced civilization inevitably creates the technology that leads to its own destruction, whether through war, environmental collapse, or something we have not yet imagined. Another possibility is the zoo hypothesis. Maybe advanced civilizations are out there and they are aware of us, but they have deliberately placed our solar system in a kind of cosmic quarantine. They are observing us, letting us develop without interference, following a universal rule of non-interference until we reach a certain level of maturity. Or perhaps interstellar travel or communication is simply far more difficult than we think, constrained by laws of physics we do not yet understand, leaving every civilization isolated on its own island world. The most humbling answer of all might be that we are truly alone, that the spark of technological intelligence is an extraordinarily rare and fragile flame in a dark, silent universe. Each explanation carries its own weight of cosmic loneliness or existential dread. This paradox forces us to confront not just the possibility of others, but the ultimate fate and significance of our own civilization in the grand, silent scheme of things. While the Fermi paradox speaks to a cosmic silence, the universe occasionally shrieks. These are not the deliberate, narrowband signals we hope for, but violent, explosive bursts of raw energy that flash across billions of light years and vanish in the blink of an eye. They are called fast radio bursts. The first was discovered in 2007, hidden in archival data from a radio telescope in Australia. It was a spike of radio waves so intense and so brief, lasting just 5 milliseconds, that astronomers initially dismissed it as terrestrial interference, perhaps a glitch from a nearby microwave oven. But then more were found. These bursts pack a staggering amount of energy, with a single millisecond flash releasing as much power as our sun emits over 3 entire days. And they are coming from incredibly deep space, far beyond our own galaxy, meaning their source must be cataclysmic. For years, every new detection was a one-time event, a cosmic flashbulb popping once in the darkness and never again. This made them nearly impossible to pinpoint and even harder to explain. Theories ranged from the collisions of ultra-dense neutron stars to the final, dying gasp of a black hole swallowing a star. Then, in 2016, everything changed. Astronomers found a fast radio burst that repeated. It was not a one-off explosion, but a source that could fire off multiple bursts, sometimes in a frantic, unpredictable pattern. This single discovery ruled out any model that involved a source destroying itself, like a stellar collision. The repeater led us to a specific galaxy, a modest, faint dwarf system over 3 billion light-years away. Now we had an address, but the mystery only deepened. What natural object could survive such a titanic release of energy, not once but over and over again? The prime suspect today is a type of neutron star with a magnetic field so powerful it could strip the information from a credit card from a distance halfway to the moon, an object called a magnetar. Some models suggest these bursts could be caused by starquakes on the magnetar's crust or by magnetic field lines snapping and reconnecting in violent events. Yet, the extreme distances and the mind-boggling energy involved still strain these explanations. The sheer power required for us to detect a millisecond pulse from another galaxy is almost incomprehensible. Of course, the sheer extremity of the phenomenon invites more speculative ideas. Could they be power beams from alien light sails propelling vast interstellar spacecraft, or perhaps signatures of some technology we cannot yet conceive? While most scientists lean toward natural, if exotic, astrophysical engines, the truth is that fast radio bursts represent a new and utterly extreme class of cosmic event. They are the universe's most powerful and enigmatic radio transmitters, broadcasting their brief, deafening messages across intergalactic space, and we are only just beginning to learn their language. Even the silent, robotic explorers we send into the void have returned with stories of cosmic unease. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were trailblazers, the first human-made objects to visit the outer gas giants and then to embark on a one-way journey into interstellar space. For decades after their primary missions ended, NASA scientists continued to track their faint radio signals, using the precise Doppler shift of these signals to measure their speed and position with incredible accuracy. And that is when they found the anomaly. Both spacecraft, billions of miles from the Sun and traveling in opposite directions, were experiencing a tiny, unexplained deceleration. It was a minuscule pullback toward the Sun, a constant, gentle braking force equivalent to about 10 billion times weaker than the gravity we feel on Earth. To put that in perspective, it was like the spacecraft were being slowed by a force no stronger than the weight of a single grain of sand resting on your palm. Yet it was there, persistent, and it defied all standard calculations. The immediate suspicion was that it was an onboard effect. Perhaps it was the gentle pressure of thermal radiation, the heat emitted by the spacecraft's own electronics and nuclear power source pushing back against the direction of travel like a soft photon breeze. Teams of engineers and physicists spent years building exquisitely detailed thermal models of the spacecraft, tracing every watt of power and every possible path of emitted infrared radiation. In the end, they concluded that a large portion, perhaps most, of the anomalous deceleration could indeed be explained by this thermal recoil force. Case closed, it seemed. But a whisper of doubt remains. Some analyses suggest that not all of the Pioneer anomaly can be so neatly accounted for. The data retains a faint residual glitch, a tiny signal that stubbornly resists being fully erased by the thermal explanation. This lingering mystery, however small, holds profound significance. It forced us to look with extreme precision at every conceivable mundane factor, pushing the limits of our engineering models. More importantly, it opened the door, even if just a crack, to the possibility of new physics. Could it be a sign of a subtle modification to the laws of gravity over vast distances? A hint that Einstein's theory of general relativity needs a tiny adjustment in the deep, quiet reaches of interstellar space? Or perhaps evidence of something more exotic, like the gravitational pull of unseen, diffused dark matter within our own solar system? While the official verdict leans toward a thermal solution, the Pioneer anomaly stands as a powerful lesson. It teaches us that even the most precise journeys into the cosmos can return with unanswered questions, that the universe might be whispering its secrets through the faint, drifting signals of our oldest mechanical ambassadors, and that sometimes the smallest deviations can point toward the largest revolutions in understanding. The silent drift of the Pioneer probes was not the only time our spacecraft reported a cosmic accounting error. There is another, more specific glitch that occurs not in the deep quiet of interstellar space, but in the bustling orbital neighborhood of our own planet. It is called the flyby anomaly. When scientists send a spacecraft on a grand tour of the solar system, they often use a technique called a gravity assist or a slingshot maneuver. The idea is elegant: to steal a tiny bit of momentum from a planet's own orbital motion. A probe approaches a planet from behind, and as it swings around, the planet's gravity whips it forward, flinging it toward its next target at a higher speed. The mathematics for this are precise, a beautiful dance of orbital mechanics perfected over decades. Yet, during certain Earth flybys, the final speed of the spacecraft has not matched the predicted speed. The discrepancy is tiny, a fraction of a millimeter per second, but in the world of deep space navigation, where a centimeter per second error can mean missing a target by thousands of miles over a multi-year journey, it is a glaring problem. This anomaly first showed itself clearly with the Galileo spacecraft in 1990. As it swung by Earth to gain momentum for its journey to Jupiter, tracking stations found its velocity was about 4 millimeters per second faster than all the complex models said it should be. Then it happened again with the Near-Shoemaker probe in 1998, which gained an unplanned extra 3 millimeters per second during its Earth flyby. Other missions like Rosetta and Messenger showed similar, though smaller, unexplained velocity shifts. It was as if the spacecraft were receiving a mysterious, minuscule push during their closest approach to Earth. The immediate suspects were all the messy, real-world factors that pure physics equations sometimes gloss over. Could it be atmospheric drag, even at high altitudes, the pressure of solar radiation, or perhaps subtle tidal effects from Earth's shape, which is not a perfect sphere but a slightly squashed oblate spheroid? Teams of engineers accounted for all of these, modeling the atmosphere, the sunlight, and Earth's bulge with incredible precision. Yet a small residual discrepancy stubbornly remained. This persistence has led to more exotic proposals. Some physicists have wondered if it is a sign of a flaw in our understanding of gravity itself. perhaps a hint that Einstein's theory of general relativity needs a tiny, situation-specific modification that only becomes noticeable during these very specific high-speed, close-approach scenarios. Others have looked to more conventional but subtle effects, like the way Earth's rotating mass drags spacetime around with it, a phenomenon called frame dragging, though the predicted effect from this is much smaller than the observed anomaly. There is even the speculative idea that Earth is surrounded by a diffuse halo of dark matter, and the spacecraft plowing through it experiences a tiny, additional gravitational tug. The flyby anomaly stands as a testament to a humbling truth that even in our own celestial backyard, with missions we have planned and executed with breathtaking accuracy, the universe can still present a receipt that does not quite add up. It is a whisper from the machinery of gravity itself, suggesting that for all our mastery of orbital equations, there may still be a line in the cosmic code we have not yet read. The subtle nudges on our own spacecraft hint at forces we do not fully grasp, but sometimes the cosmos presents a mystery on a scale so vast it defies all convention. Far away in the constellation Cygnus, a star named KIC 8462852, but better known as Tabby's star, is doing something impossible. Discovered by citizen scientists in the Kepler Space Telescope data, this otherwise ordinary star exhibits light curves unlike anything ever seen. Planets transit stars, causing predictable, symmetrical dips in brightness as they pass in front. Tabby's star does not do that. Its light drops by staggering amounts, up to 22% at times, in chaotic, asymmetrical, and utterly irregular patterns. These are not the gentle, repeating shadows of planets. These are deep, jagged eclipses that sometimes last for days, sometimes for weeks, with no discernible rhythm. The first instinct was to look for a natural culprit, perhaps a colossal cloud of dust and debris from a recent planetary collision. But the star shows no excess infrared heat, the telltale signature of warm dust that such a catastrophic event would produce. The dimming is too severe, too messy, and too intermittent. One of the more plausible natural explanations involved a vast, swarming family of giant comets, thousands of them, passing in front of the star in a chaotic ballet. This could, in theory, create the irregular dimming. Yet, to block that much light, the comet swarm would have to be impossibly large and dense, a scenario that stretches the limits of what we believe is possible in a mature solar system. The absence of that warm dust glow remained a persistent problem for any dusty explanation. It was this very strangeness that led to a wild, thrilling, and deeply controversial hypothesis. Could we be seeing the shadows of alien megastructures? The concept, first proposed by physicist Freeman Dyson, imagines an advanced civilization capturing the entire energy output of its star by building a vast swarm of orbiting collectors, a Dyson sphere. A partially completed or disorganized swarm could create exactly the kind of bizarre, deep, and irregular light dips we observe. For a moment, the scientific world held its breath, not because anyone believed it was likely, but because the data was so stubbornly weird that even an extraordinary idea had to be on the table. Subsequent observations have poured cold water on the most exciting possibilities, but have not solved the mystery. Detailed studies of the star's light at different colors show that blue light is blocked more than red light. This is a classic signature of dust, not solid objects. A solid megastructure would block all colors equally, so the leading theory now points back to dust, but of a very peculiar kind. Perhaps it is fine, microscopic dust with unusual properties, or dust trapped in a strange orbital configuration we have never seen before. Some suggest the star itself is unstable, sporadically belching out clouds of material that then occult its own light. Yet the star appears normal in every other way, not given to such extreme tantrums, so we are left with a profound cosmic riddle. Tabby's star is likely shrouded in a strange, complex, and dynamic cloud of dust that we cannot fully explain with our current models of solar system formation or stellar behavior. It is a reminder that nature's imagination far exceeds our own, capable of constructing puzzles for which we do not yet have all the pieces. The alien megastructure hypothesis may have faded, but in its place remains something just as compelling, a genuine astrophysical phenomenon that simply does not add up, a single star whose flickering light holds a secret we are still learning how to read. Our own star's strange flickers are a local mystery, but to find the oldest and largest imprint on reality, we must look far beyond any single sun to the very edge of observable time. This brings us to the cosmic microwave background, the afterglow of the Big Bang itself. It is the oldest light in the universe, a faint, cold glow that fills every direction of space, a snapshot of the infant cosmos when it was just 380,000 years old. For the most part, this primordial map is remarkably uniform, a testament to the smooth, hot soup of the early universe. But within this smoothness, there are tiny, expected fluctuations, the seeds from which all galaxies would eventually grow. And then there is the cold spot. It is not a tiny fluctuation. It is a colossal region of space spanning over 1 billion light-years across, where the background radiation is significantly colder than the surrounding average. Statistically, it is an extreme outlier, a feature so large and so cold that it challenges the standard model of cosmology, which predicts a more even distribution of such variations. It is as if you laid out a vast, subtly patterned tapestry, only to find a single, unmistakably dark and frigid patch woven into the fabric. The most straightforward explanation is that it is a cosmic supervoid, an immense bubble of mostly empty space lying between us and the cold spot. As light travels through such a void, it loses a tiny amount of energy climbing out of the underdense region's gravitational well, a process that can slightly cool the light we receive, an effect known as the integrated Sachs-Wolf effect. Astronomers have searched for this proposed supervoid. They have found some underdense regions in that direction, but nothing nearly vast or empty enough to account for the profound coldness we observe. The scale simply does not match. The void we see is not void enough. This mismatch has forced cosmologists to consider far more exotic possibilities. One of the most mind-bending is the idea that the cold spot is a bruise, a cosmic scar from a collision with another universe. In certain multiverse theories, our universe is one bubble in a frothing sea of eternal inflation, where new universes constantly bud off from a primordial background. If our bubble universe had a glancing collision with another bubble in the distant past, the energy released at the boundary could have left a distinct circular imprint on the cosmic microwave background, a region of unusual temperature. The cold spot, some suggest, has the right profile for such an imprint. It is a staggering thought that we might be looking at direct evidence of a parallel cosmos brushing against our own in the first moments of creation. Of course, this remains highly speculative, and other theories propose more conventional, if still poorly understood, physical processes in the early universe that could create such a large anomaly. Yet its persistence is what makes it so compelling. The cold spot refuses to be explained away. It sits on our most ancient map of all things, a billion light-year wide question mark. It whispers that even our best understanding of the universe's birth and evolution might be missing a crucial chapter, one written in the language of profound, cold, and staggering scale. A chapter that could contain anything from a missing supervoid to the fingerprint of another reality entirely. If the cold spot is a bruise on the ancient sky, then the so-called axis of evil is a crack running through its very foundation. It begins with a core principle of modern cosmology, the cosmological principle. This is the grand, democratic assumption that the universe on the largest scales is isotropic and homogeneous. In plain language, it means the cosmos should look the same in every direction, with no preferred center and no special axis. There should be no up or down, left or right in the grand scheme of things. This principle is the bedrock upon which we built our entire understanding of the Big Bang and cosmic evolution. Then we mapped the cosmic microwave background with exquisite precision, and something deeply unsettling emerged. When scientists analyzed the subtle temperature fluctuations in that ancient light, they found hints of a pattern, an alignment that should not be there. The largest scale fluctuations in the microwave sky appear to be oddly correlated with the plane of our own solar system, the ecliptic, and even the direction of the sun's motion through the galaxy. It is as if the universe's oldest fingerprint has a faint but distinct smudge that lines up with our local backyard. This apparent correlation was so shocking and so philosophically troubling that astronomers half-jokingly dubbed it the axis of evil. The name captures the profound threat it poses to our standard model. If this alignment is real and not a statistical fluke or an artifact of how we process the data, it means one of two terrifying things. Either the universe on its largest scales is not isotropic, not the same in all directions, which would force us to abandon a cornerstone of cosmology, or our position in the cosmos is strangely special, a direct violation of the Copernican principle that states we do not occupy a privileged place. The implications are staggering. It could suggest that the structure of the entire observable universe has a preferred direction, a cosmic axis, and by some impossible coincidence, our little solar system is aligned with it. The debate has raged for years. Skeptics argue vigorously that the effect is a subtle systematic error, a contamination from our own galaxy's foreground light that hasn't been perfectly cleaned from the maps, or even a trick of the statistical methods used. Every new data release from satellites like Planck is scrutinized for this anomaly, and while some signatures have weakened, hints of the alignment stubbornly persist. It refuses to be completely erased. This is not just a technical argument among astrophysicists, it is a battle for the soul of our cosmic worldview. Are we truly seeing a fundamental flaw in our understanding of the universe's symmetry, a crack in the cosmological principle itself, or are we merely seeing the ghost of our own reflection in the data, a persistent illusion born from our limited perspective? The axis of evil remains a profound and unresolved tension, a whisper in the oldest light that we might, against all odds, be looking at the universe from a place that is not just a random point in an endless, uniform void. The universe's earliest moments were a forge of creation, but the account books from that time contain a glaring error. In the first 3 minutes after the Big Bang, a process called Big Bang nucleosynthesis fused the primordial soup of protons and neutrons into the first light elements, hydrogen, helium, and a tiny trace of lithium. The amounts of hydrogen and helium we see in the oldest stars match the theoretical predictions with stunning precision, a cornerstone triumph for the Big Bang model. But lithium is a different story. The universe seems to have produced only about 1/3 of the lithium-7 isotope that our models insist should be out there. This is the lithium problem. We are not talking about a small rounding error. The calculations are precise, based on well-understood nuclear physics and the measured density of ordinary matter in the cosmos. Yet when astronomers look at the ancient, metal-poor stars in the halo of our galaxy, stars that formed from nearly pristine material from the early universe, they find their atmospheres contain consistently 2 to 3 times less lithium than the Big Bang recipe calls for. It is as if someone went through the cosmos and systematically removed this specific element from the oldest stellar vaults. This missing lithium forces a difficult choice. Either our understanding of nuclear physics in the universe's first 3 minutes is incomplete, or something has been destroying lithium in these ancient stars for billions of years. The first possibility leads us down a fascinating rabbit hole of new physics. Could unknown particles, like certain types of dark matter, have been present in that primordial furnace, altering the nuclear reaction rates just enough to produce less lithium? It is a tantalizing idea, using a cosmic accounting error to probe physics beyond the standard model. The second possibility focuses on stellar astrophysics. Perhaps these ancient stars, though superficially simple, have internal processes that slowly drag surface lithium down into their hot interiors where it is destroyed. Convection, rotation, or magnetic fields could be the culprits, acting as a cosmic lithium shredder. The challenge is that no single stellar model convincingly explains the uniform depletion seen across so many different stars. The lithium problem persists because both solutions create their own complications. Invoking new particles feels like using a sledgehammer to crack a nut, while stellar destruction mechanisms struggle to match the precise, consistent depletion we observe. It is a quiet but profound contradiction, a single line in the ledger of creation that refuses to balance, reminding us that even our most successful cosmic stories may still have missing pages. The quiet imbalance of lithium in the ancient universe speaks of subtle, hidden processes, but the cosmos also hurls projectiles of pure, violent contradiction directly at us. These are ultra-high-energy cosmic rays, not rays of light but single atomic nuclei, often just a lone proton, accelerated to velocities that defy belief. Their energy is almost incomprehensible. A single one of these subatomic bullets can carry the kinetic energy of a professionally thrown baseball, all compressed into a particle a trillion times smaller than a grain of sand. They possess millions of times more energy than anything we can create in our most powerful particle colliders like the Large Hadron Collider. They are the universe's ultimate particle accelerators, operating on a scale we cannot replicate. And that is where the mystery begins. According to our understanding of physics, such particles should not be able to travel very far through the cosmos at all. Space is not empty, it is filled with the faint glow of the cosmic microwave background, that sea of ancient photons left over from the Big Bang. For a proton traveling at over 99.9999% the speed of light, these low-energy microwave photons appear as a dense fog of high-energy gamma rays. The ultra-high-energy proton will inevitably collide with these photons, a process that saps its energy, slowing it down dramatically over distances of a few 100 million light-years. It is called the GZK cutoff, named for the physicists who predicted it. This means any such cosmic ray we detect here on Earth should have originated from within our local cosmic neighborhood, within a relatively short distance on the universal scale. Yet when astronomers trace back the paths of the most extreme events, their trajectories often point to empty voids of intergalactic space, with no obvious powerhouse source like a galaxy or a black hole anywhere nearby. It is as if a cannonball were fired at you from across a battlefield, but when you look back, you see no cannon. So what cosmic engines are capable of launching these particles with such ferocious energy? The prime suspects are the most violent objects we know. Active galactic nuclei, where supermassive black holes devour matter and blast out jets of plasma moving at nearly the speed of light, could potentially accelerate particles to these extremes. Cataclysmic events like the merger of neutron stars or the explosive death of a hypernova are also candidates, but the alignment problem remains. Many of the detected rays do not point back to such spectacular sources. This has led to more radical ideas. Could these particles be the decay products of exotic, super-heavy dark matter particles, annihilating or decaying in the halo of our own galaxy? If so, they would not have traveled far, neatly sidestepping the GZK distance problem. Or perhaps our models of particle physics or the behavior of spacetime itself need revision at these extreme energies. Every time one of these rare particles slams into Earth's atmosphere, creating a vast cascade of secondary particles we can detect, it asks a profound question. What unimaginable violence or what hidden flaw in our laws of physics is required to fire a single proton across the universe with the force of a fastball? But if dark matter is the universal glue, what happens when we find a galaxy built without it? This is not a theoretical puzzle, it is a real place, a ghostly galaxy called NGC 1052 DF2. Discovered in 2018, this galaxy is a cosmic paradox made flesh, or rather, made stars. It is an ultra-diffuse galaxy, a vast, wispy cloud of stars so spread out you can almost see right through it. Yet its stars are old, indicating a quiet, stable history. When astronomers measured the motions of its star clusters to weigh the galaxy, they expected to find the familiar signature of dark matter's hidden mass. Instead, they found nothing. The visible stars were moving at speeds that could be entirely explained by their own gravity alone. There was no extra pull, no phantom scaffold. This galaxy appeared to be made of normal matter and normal matter only. The discovery sent shockwaves through astrophysics. For decades, dark matter was not just a theory, it was the foundational ingredient in our recipe for galaxy formation. The prevailing model said that dark matter halos formed first, their gravity drawing in gas which then cooled and condensed to form stars. A galaxy without dark matter should not exist, or at least should not be stable. It was like finding a towering sandcastle built without any sand, standing defiantly against the tide. The immediate response was intense scrutiny. Could the measurements be wrong? Perhaps the galaxy was oriented in a tricky way that masked the true stellar speeds. Or maybe the dark matter was there, but distributed in a halo so vast and diffuse that its gravitational signature at the galaxy's core was undetectable. Follow-up observations with more powerful telescopes confirmed the initial result. The star motions were slow, the mass was accounted for by visible stars, and the dark matter was missing. This forced a profound debate. One camp saw this as a potential crisis for dark matter theory itself. If the theory is correct, how could such an object form? The other camp saw it as a fascinating clue to a more complex story. Perhaps NGC 1052DF2 is a tidal dwarf galaxy, a shred of stars ripped away during a violent collision between two larger galaxies. In such a scenario, the dark matter, which forms a more spread-out halo, might be left behind while the dense, gas-rich cores of the colliding galaxies get stripped out to form a new dark matter-free object. Intriguingly, this galaxy lies near a massive elliptical galaxy, a plausible site for such a past encounter. The implications are staggering either way. If it is a tidal dwarf, it proves that galaxies can, under extreme conditions, form from normal matter alone, offering a new laboratory to test our ideas about gravity and structure. If it is a primordial galaxy that somehow never acquired dark matter, it challenges the very framework of how we believe the universe builds its largest structures. This single, ghostly galaxy became a cosmic litmus test. It does not disprove dark matter, but it insists that our story of galaxy formation must have more chapters, more exceptions, and more strange pathways than we ever imagined. The ghostly galaxy without dark matter shows our cosmic models can be wrong, but another discrepancy strikes at the very heart of how we measure the universe's most fundamental behavior. This is the Hubble tension, and it is a crisis of precision. For over a century, we have known the cosmos is expanding. The rate of that expansion is called the Hubble constant, a single number that tells us how fast space is stretching at a given distance. Pinpointing this number is arguably the most important task in cosmology, as it tells us the age, size, and ultimate fate of everything. Today, we have two supremely precise, completely independent ways to measure it. And they give us two different, stubbornly incompatible answers. It is as if you used two flawless stopwatches to time the same race, and each one gave you a different, definitive winner. The first method looks back to the dawn of time, using the cosmic microwave background. By analyzing the subtle patterns in that ancient afterglow with satellites like Planck, cosmologists can work backwards through the entire history of the universe, applying our well-tested models of dark matter and dark energy to predict what the expansion rate should be right now. This is a top-down, early universe approach. The other method builds from the bottom up using local distance markers. astronomers observe specific types of stars and supernova in nearby galaxies, whose intrinsic brightness we know, allowing us to measure their distance with great accuracy. By then measuring how fast those galaxies are moving away from us, we can calculate the Hubble constant directly in the present-day universe. Both methods have been refined to an extraordinary degree, with error margins so small they are represented by tiny, non-overlapping bars on a graph. And those bars do not touch. The early universe method suggests a slower, more sedate expansion rate, around 67 kilometers per second per megaparsec. The local, late universe method insists on a faster, more frenetic pace, closer to 73. This is not a small statistical fluke. The gap is now so significant that the chance of it being a simple error is less than 1 in a million. This tension is not just a mathematical curiosity. It is a direct signal that something in our standard model of cosmology is incomplete or incorrect. We are missing a piece of physics. One compelling possibility is that dark energy, the force driving the acceleration of the cosmos, is not a constant as we have assumed. Perhaps it is dynamic, changing in strength over the history of the universe. If dark energy was slightly stronger in the past or is interacting with dark matter in an unknown way, it could alter the expansion history just enough to reconcile the two measurements. Another line of thought points to the early universe itself. Could there have been an extra type of radiation, like a new, lightweight species of neutrino, that zipped through the primordial soup and altered its expansion dynamics in the first few moments? This would change the calculations derived from the cosmic microwave background without affecting the local measurements we make today. More exotic ideas even suggest that the fabric of space-time might have subtle lumps or variations in density on scales larger than we can observe, throwing off our cosmic yardsticks. The Hubble tension is more than a puzzle, it is a beacon. It tells us that our otherwise spectacularly successful model of the universe, lambda cold dark matter, has a crack running through its foundation. Every new observation, every more precise measurement of a distant supernova or a flickering star tightens the vise. This is not a failure of science, but its ultimate expression, the moment where exquisite data forces a revolution. We are being told by the universe itself that we are on the verge of discovering something profound, a new ingredient or a new rule that governs the expansion of all reality. The two most precise measurements we have ever made are arguing with each other, and the resolution of that argument will rewrite our cosmic story. The Hubble tension is a crisis of numbers, but the cosmos also presents us with voids of staggering emptiness. Between the glittering filaments of the cosmic web, the vast superclusters of galaxies, lie the opposite, immense regions of near-nothingness called supervoids. These are not just slightly emptier patches of space, they are cosmic deserts on a scale that defies belief, some stretching over 1 billion light-years across. Within them, galaxies are almost non-existent, making them the largest single structures in the entire universe. Their existence is expected. Our models of the Big Bang and dark matter predict that gravity will pull matter into dense knots, leaving behind empty bubbles. But the supervoids we are finding are too big and far too empty. According to our most sophisticated computer simulations of cosmic evolution, voids of this scale and purity should be incredibly rare cosmic unicorns. Yet our telescopes keep finding them. It is as if we built a model of how foam forms, only to look at the ocean and see bubbles 10 times larger than our theory says are possible. This presents a direct challenge to our understanding of structure formation. If dark matter and gravity worked exactly as we think, the universe should look lumpy, but not this lumpy. These profound emptinesses suggest that either dark matter behaves in a stranger way, clumping together even more strongly than predicted and leaving behind cleaner voids, or that another force is at work, actively evacuating these regions. This is where the mystery deepens and connects to other cosmic puzzles. Remember the cold spot in the cosmic microwave background, that billion light-year-wide patch of unusual cold? One of the leading explanations was that it was caused by a supervoid, a vast underdensity of matter that the ancient light traveled through, losing energy and cooling slightly. The hunt was on, and astronomers did find a large void in that general direction, but it was not nearly vast or empty enough to explain the profound coldness of the spot. This mismatch is the heart of the issue. The voids we see are not void enough to account for the effects we measure. This points to something invisible at work within the emptiness itself. Could dark energy, the force accelerating cosmic expansion, be stronger inside these voids? In the standard model, dark energy is a constant, the same everywhere. But if it were slightly stronger in regions of extreme low density, it could act as a cosmic vacuum pump, more aggressively pushing matter out of the voids and smoothing them to an even greater degree. This would create the oversized emptinesses we observe and could also amplify the cooling effect on the cosmic microwave background, potentially solving the cold spot mystery in one stroke. Alternatively, it might mean our law of gravity, Einstein's general relativity, needs modification on the largest scales. Perhaps gravity behaves differently in near-total vacuums, weakening just enough to prevent matter from falling back in, leaving these regions perpetually barren. These supervoids are more than just empty space. They are negative sculptures in the cosmos, carved by forces we do not yet fully understand. By studying the shape and scale of nothing, we might find the key to everything, revealing the true character of the dark components that shape our universe. The profound emptiness of supervoids forces us to question the very nature of cosmic nothingness, but on a far closer and more personal frontier, a different kind of emptiness holds a tantalizing secret. The thin, cold air of Mars is whispering to us, and its message is written in a simple molecule, methane. Detected intermittently by rovers like Curiosity and orbiters like the European Space Agency's Mars Express, these whiffs of gas are a planetary-scale enigma. On Earth, a significant portion of atmospheric methane is produced by biological activity, from microbes in soils to the digestive systems of animals. Its presence on Mars immediately raises the electrifying possibility of life, past or present, hidden beneath the rust-colored soil. But the mystery is far more complex than a simple detection. Sunlight and chemical reactions in the Martian atmosphere should break methane apart within a few hundred years. Finding any methane at all means it is being replenished, that there is an active, ongoing source somewhere on the planet right now. It is as if you walked into an ancient, sealed attic and caught the faint, fresh scent of bread baking, a sign that the house is not as empty as it seems. The puzzle deepens with the gas's bizarre behavior. It does not linger as a constant global blanket. Instead, it appears in sudden, localized plumes that spike in concentration and then vanish, sometimes seasonally, sometimes at random. The Curiosity rover has even recorded a daily cycle, with methane levels rising at night and falling during the day. This sporadic, patchy nature suggests the source is localized and possibly episodic, and that the methane is being destroyed or sequestered near the surface with shocking speed, a process we do not fully understand. So what is producing it? Scientists have two broad categories of explanation: geological and biological. The leading geological candidate is a process called serpentinization. When certain types of rock, like olivine, come into contact with water deep underground, a chemical reaction can occur that produces methane as a byproduct. This requires no life, just the right chemistry and liquid water, which we know exists in subsurface Martian ice. Alternatively, methane could be released from ancient clathrate deposits, icy cages of methane trapped underground that occasionally rupture. The biological hypothesis, of course, is that microbial life, perhaps dwelling in deep, salty aquifers safe from surface radiation, is metabolizing and producing the gas as a waste product, just as methanogens do on Earth. The maddening and compelling part is that with our current data, we cannot yet distinguish between these possibilities. Each new detection is a clue, but the evidence remains frustratingly circumstantial. The sporadic nature itself is a key piece of the mystery, pointing to a dynamic, hidden Martian subsurface that occasionally vents its secrets into the thin air. Is Mars a geologically active world, quietly cooking methane in its rocky depths, or is it a living world, harboring simple organisms in its last hidden refuges? Every faint, intermittent spike on a spectrometer brings us closer to an answer that would fundamentally reshape our place in the cosmos. The faint chemical whispers from Mars are a local mystery, but in October 2017, our solar system received a visitor from a place impossibly far beyond. The Pan-STARRS telescope in Hawaii spotted a faint dot of light moving at breathtaking speed. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. This was no asteroid from our backyard. It was our first confirmed interstellar tourist, and we named it Oumuamua, Hawaiian for scout. The data that followed painted a portrait of an object unlike anything in our own solar system. First was its shape. By measuring how its brightness changed as it tumbled, astronomers deduced it was highly elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a flattened pancake. This was unusual, as most solar system objects are more lumpy or spherical, but the real anomaly came as it sped away from the sun. After its slingshot around our star, Oumuamua should have coasted, slowly decelerating under the sun's persistent pull. Instead, it sped up. This non-gravitational acceleration was small but definitive, and it demanded an explanation. For comets, such a boost is common, caused by outgassing. As the comet's icy nucleus heats up near the sun, it vents jets of gas and dust which act like a natural rocket engine pushing the comet along. The telltale sign of this activity is a coma, a fuzzy envelope of gas and dust, and often a tail. Oumuamua had neither. No dust cloud, no gas emissions were detected by our most sensitive instruments. It presented a stark, rocky silhouette against the void, yet something was propelling it. The scientific community scrambled for a natural explanation. One leading idea proposed that Oumuamua was made of molecular hydrogen ice. This exotic substance could sublimate, turning directly from solid to gas under the sun's warmth, providing a thrust without producing the dusty coma typical of water ice comets. The problem is that hydrogen ice is incredibly fragile, likely unable to survive a long journey through interstellar space. Another suggestion was that it was a shard of a Pluto-like world, a chunk of nitrogen ice that eroded away during its passage, again providing stealthy propulsion. Yet these models felt like forcing a square peg into a round hole, constructed specifically to explain this one bizarre object. The sheer strangeness of its characteristics, a shape unlike our asteroids, acceleration without a visible coma, and its interstellar origin led some scientists, most notably Harvard astronomer Avi Loeb, to openly speculate about an artificial origin. Could it be a light sail, a piece of alien technology using radiation pressure from the sun for propulsion? This was not a claim of discovery, but a statement about the limits of our categories. Oumuamua did not fit the profiles we had spent centuries building. It was a genuine anomaly, a data point from a cosmic catalog we have not yet written. Whether it was a strange new type of icy asteroid, a fragment from a shattered world, or something else entirely, its brief passage was a profound reminder. The universe is capable of constructing objects that defy our expectations, and our first messenger from the stars left us with more questions than answers. The search for cosmic engineering does not end with a single, silent visitor. It continues in the flickering light of distant stars, where patterns emerge that defy easy classification. Among these, a star catalogued as Epic 204278916 stands out, not for a single dramatic dip like Tabby's star, but for a staggering series of them. Over a 78-day observation period by the Kepler Space Telescope, this young, sun-like star dimmed by up to 65% for days at a time in a chaotic, unpredictable rhythm. The shadows crossing its face were not the clean, symmetrical transits of planets, but deep, jagged, and irregular eclipses. This star, and others like it discovered in the torrent of data from Kepler and its successor, TESS, represent a new class of cosmic mystery, often called Dyson sphere candidates. The hunt for these anomalies is a monumental task, a needle in a haystack search through the light curves of hundreds of thousands of stars. It is a pursuit powered by a unique partnership between professional astronomers and a global army of citizen scientists. Platforms like Planet Hunters allow volunteers from around the world to examine telescope data by eye, their human pattern recognition often spotting the weird, messy dips that automated algorithms are trained to ignore. These flagged stars then become targets for intense professional scrutiny, their light analyzed across every wavelength from infrared to ultraviolet in a forensic attempt to diagnose the cause. In nearly every case so far, the most plausible explanations are natural, albeit spectacularly messy. The leading suspect is circumstellar dust, but not in a simple, serene disk. Imagine a young solar system in a state of violent chaos, with swarms of comets, colliding protoplanets, and immense clouds of debris orbiting in clumpy, eccentric rings. As these vast, uneven dust clouds pass in front of their star, they could create the deep, irregular dimming we observe. The star epoch 204278916, for instance, is very young, still surrounded by the primordial material from its formation, making such extreme dust activity more likely. The absence of certain chemical signatures in the starlight often points to dust as the culprit, as tiny particles scatter blue light more than red. Yet, it is the sheer extremity of the data that keeps a more thrilling possibility on life support. The depth and irregularity of the dimming push some natural models to their limits. Could a dust cloud really be that opaque and that misshapen? When every natural explanation feels like a stretch, the mind wanders to the visionary concept of a Dyson swarm. This would not be a solid shell, but a vast, incomplete constellation of energy collecting panels in orbit around a star, their chaotic arrangement casting a complex, shifting shadow. Such a structure, built by a civilization harnessing the total power of its sun, would produce a light curve that is asymmetric, aperiodic, and profoundly strange, exactly like the data we struggle to explain. These stars are not proof, they are provocations. They represent the outer boundary of what we know natural systems can do, and in that ambiguity lies their power. They force us to ask, at what point does an explanation become more fantastical than the fiction it seeks to replace? A perfectly engineered swarm of solar panels, or a never-before-seen scale of natural cosmic debris. These flickering points of light keep the most profound question in science alive, not by answering it, but by refusing to let us look away. The search for hidden giants does not stop at the edge of a star's light. It continues right here in the frozen darkness of our own cosmic backyard. Far beyond Neptune, in a region called the Kuiper Belt, a collection of icy worlds follows orbits that tell a strange and consistent story. These are not random paths. A group of these most distant objects, with orbits taking thousands of years to complete, share a peculiar alignment. Their elliptical paths are clustered together in space, their points of closest approach to the Sun, their perihelia, bunched up in the same general direction. Furthermore, their orbits are tilted in a similar way, as if a shepherd is keeping them in a specific celestial pasture. According to the laws of gravity, this clustering should not happen naturally. Over the age of the solar system, the gentle gravitational tugs from the known giant planets should have randomized these orbits, scattering their orientations. The fact that they remain grouped is a powerful clue, a signpost pointing to a massive, unseen presence. The simplest explanation is a planet, a world several times more massive than Earth, orbiting the Sun on a distant, tilted path of its own. Its gravitational influence over billions of years could have herded these distant icy bodies into the peculiar alignment we see today. This hypothetical world is called Planet 9. The evidence is entirely indirect, a ghostly signature written in the paths of smaller objects. Astronomers have been conducting a painstaking digital hunt, scanning the deepest, darkest skies for a faint point of light moving slowly against the backdrop of fixed stars. The challenge is immense. Planet 9, if it exists, would be incredibly far away, perhaps 20 times farther from the Sun than Neptune is. At that distance, it would receive almost no sunlight and reflect virtually none back to us, making it fantastically dim. Its orbital period could be as long as 20,000 years, meaning it moves at a glacial pace across our sky, requiring years of observations to confirm its motion. The controversy lies in the nature of the evidence itself. Could the orbital clustering be a trick of observation, a bias because we have only found the objects that are easiest to see from our particular vantage point? Critics argue that more complete surveys might reveal the clustering to be an illusion. Yet, as more of these extreme Kuiper belt objects are discovered, the pattern has, if anything, grown stronger. The existence of Planet 9 would be a monumental discovery, forcing a complete rewrite of our solar system's history. It would mean our planetary family is not the neat, compact system we once thought. How did such a large world get flung so far out? One compelling theory suggests it formed closer to the Sun, alongside Jupiter and Saturn, and was violently ejected during the chaotic early days of the solar system, only to be captured in a wide, stable orbit by the gravity of the passing galactic tide. Its presence would also explain other solar system oddities, like why the plane of the planets is tilted relative to the Sun's equator. We are left with a profound possibility that a true giant, a major world, still hides in the perpetual twilight just beyond our vision, its gravity the only hint of its silent, patient orbit. Deep in the heart of our own Milky Way, a silent, invisible fire burns. This is the galactic center excess, a mysterious fog of high-energy gamma-ray light that bathes the core of our galaxy in a radiation we cannot see with our eyes. It was the Fermi Gamma Ray Space Telescope, mapping the sky in gamma rays since 2008, that first clearly revealed this strange glow. When scientists carefully subtracted all the known sources of gamma rays, from pulsars to supernova remnants, a persistent, unexplained excess remained, concentrated right at the galactic center. It is not a single point of light, but a diffuse, symmetrical haze stretching thousands of light years, a ghostly signature of something profoundly energetic happening in the crowded stellar metropolis at our galaxy's core. The hunt to identify its source has become a high-stakes detective story with two prime suspects, each pointing to a radically different understanding of the cosmos. The first and most thrilling suspect is dark matter itself. The center of the galaxy is thought to be the densest region of dark matter in the Milky Way. If dark matter particles are their own antimatter counterparts, they could annihilate upon collision, converting their mass directly into energy and producing a spray of gamma rays. The smooth, symmetrical shape of the excess matches what many models of dark matter annihilation predict. A confirmed detection here would be a monumental breakthrough, finally revealing the particle identity of the universe's dominant form of matter and opening a direct window into physics far beyond the standard model. The other leading suspect is a celestial population we know exists but have not fully catalogued: millisecond pulsars. These are the rapidly spinning, hyper-dense corpses of dead stars, beaming out lighthouse-like pulses of radiation, including gamma rays. Thousands of these faint, ancient pulsars could be clustered in the galactic center, each too dim for Fermi to see individually, but together creating a collective glow that appears as a smooth excess. This explanation is more conventional but still profound, as it would reveal a previously unseen structure of stellar remnants in our galaxy's heart. The problem is we cannot yet distinguish between these two possibilities. The gamma-ray signal does not have a clear fingerprint that says dark matter or pulsars. It is a cosmic ambiguity. To solve it, astronomers are searching for telltale clues. If it is pulsars, then next-generation radio telescopes might eventually resolve a few of the brightest point sources within the haze, breaking the smooth glow into individual dots. If it is dark matter, we might see a similar excess emanating from smaller, nearby dwarf galaxies, which are also dense with dark matter but lack the stellar population to produce many pulsars. So far, the evidence remains tantalizingly inconclusive. This makes the galactic center access a crossroads of modern science. Its resolution will either hand us the keys to the dark universe or unveil a hidden architecture of dead stars, forcing us to rewrite the demographic history of our own galaxy. Every new analysis of Fermi's data tightens the focus on this mysterious glow, a silent beacon at the center of everything we know, waiting to tell us which path to the truth is real. A ghostly chemical fingerprint is smeared across the galaxy. When astronomers point infrared telescopes at the vast clouds of gas and dust between the stars, at the glowing shells of dying stars known as planetary nebulae, and even at other galaxies, they detect a set of distinct bright emission bands. These are the unidentified infrared bands, a spectral signature that has been known for decades, seen almost everywhere we look, yet its source remains a cosmic whodunit. It is the persistent hum of a specific molecule or family of molecules that we have not yet pinned down in a laboratory on Earth. The bands are like hearing a familiar song played on an instrument you cannot identify, a tune that fills the interstellar medium but whose performer remains hidden in the wings. The prime suspect for this cosmic composer is a class of organic molecules known as polycyclic aromatic hydrocarbons, often called PAHs. Picture them as tiny, flat flakes, miniature chicken wire structures made of linked rings of carbon and hydrogen atoms. They are essentially soot, the same basic building blocks you would find in the char on a grilled piece of food or in the exhaust from a car, and in space they make a lot of sense. They are robust, able to survive the harsh radiation between stars, and when they are zapped by an ultraviolet photon from a nearby hot star, they vibrate and spin, emitting that very specific infrared glow we detect as the band. The case for PAHs is strong, but it is not airtight. The problem is in the fine details. The exact wavelengths and shapes of the observed infrared bands do not match perfectly with the spectra of any specific PAH molecule we have been able to study in labs here on Earth. It is as if we have identified the artist's general style, but every brushstroke is slightly off. The interstellar bands are smoother and broader than what our best models produce. This suggests the carrier is something related, but perhaps more complex, maybe PAHs that are partly frozen in ice mantles on dust grains, or larger, more intricate carbon networks that we have not yet synthesized. Some scientists even speculate the bands could come from completely different carbon-based structures, like tiny diamonds or onion-like fullerenes. Solving this mystery is far more than academic curiosity. These unidentified bands are a dominant feature of the infrared universe, meaning whatever is producing them is a major component of interstellar dust and organic material. They are a key piece of the cosmic carbon cycle. Carbon is the essential element for life as we know it, and these mysterious molecules are likely a crucial stepping stone in the chemical pathway that leads from simple atoms in stellar winds to complex prebiotic compounds. They are the cosmic factories producing the organic feedstock that eventually gets incorporated into new stars, planets, and potentially living systems. By identifying the exact molecule behind the bands, we would unlock a fundamental chapter in the chemical history of the galaxy. We would know what form much of the universe's carbon takes as it drifts between the stars, and we would understand a critical process in how the raw ingredients for planets and life are manufactured and distributed. The unidentified infrared bands are a ubiquitous chemical signature, a message written in the thermal glow of deep space, and we are still learning how to read it. The chemical whispers between the stars are not the only hidden messages written in the universe's invisible ink. In 2019, astronomers working with a powerful new radio telescope array called ASCAP stumbled upon something that simply should not be there. They were conducting a survey of the night sky, mapping the faint radio glow of distant galaxies, when their computers flagged perfect circles of radio emission. These were not smudges or blobs, but crisp, circular structures like ghostly bubbles blown into the fabric of space itself. They named them odd radio circles, or ORC. The first instinct was to assume they were some kind of imaging artifact, a glitch in the data processing, but repeated observations confirmed they were real. And they were enormous, each one spanning hundreds of thousands of light years across, large enough to swallow entire galaxies whole. The true shock came when astronomers pointed other telescopes, those that see in optical, infrared, and X-ray light at the same coordinates. There was nothing there. The circles were completely invisible, ghosts that only revealed themselves in the radio portion of the spectrum. It was as if someone had drawn perfect rings on the sky with ink that only one specific instrument could see. This posed an immediate and profound question: what cosmic event could create such vast, symmetrical, and transient structures, leaving no trace in any other form of light? The hunt for an explanation began, and every familiar suspect fell short. They were not the remnants of supernova explosions. Those are far too small and messy. They did not match the profile of planetary nebula, the glowing shells shed by dying stars. They were not the famous Einstein rings caused by gravitational lensing, as those would have a visible galaxy at their center. The leading theories now stretch our understanding of galactic violence. One idea is that these are the titanic shockwaves from a past event in the center of a galaxy, perhaps a starburst period where millions of stars were born and died in rapid succession, their combined stellar winds and supernova blasting a spherical bubble into the intergalactic medium. Another, more dramatic possibility points to the supermassive black hole at a galaxy's heart. If two such black holes merged in the distant past, the unimaginable energy released could have sent a spherical tsunami of radiation and particles racing outward at near light speed, its leading edge visible as a radio circle. Yet another hypothesis suggests they are the throats of wormholes, or the imprint of collisions between cosmic strings, theoretical defects in space-time itself. The most humbling possibility is that ORCs represent a brand new class of cosmic object, a phenomenon we have never seen before and do not yet have the language to describe. They are a reminder that our map of the universe is still being drawn, and every time we build a telescope that sees the sky in a new way, we risk discovering something that breaks all the old categories. These perfect radio ghosts floating in the darkness are a direct challenge, a silent announcement that the cosmos still holds entire chapters of physics waiting to be read. The ghostly signatures of unknown particles may not be confined to deep space. Sometimes they are forged in the heart of our own laboratories, hinting at states of matter so strange they could rewrite the rules of the cosmos. This brings us to the tetraneutron, a particle that should not exist. For decades, the nuclear chart has been built on a simple, stable principle. Atomic nuclei are a balance of protons and neutrons held together by the strong nuclear force. A nucleus made solely of neutrons with no protons to provide electrostatic repulsion was thought to be impossible. The nuclear forces simply would not allow it. A lone pair of neutrons cannot form a bound state, let alone a group of 3 or 4. They would fly apart in an instant, yet in 2 separate experiments, first in 2002 and then with greater confidence in 2016, physicists observed a tantalizing signal. By smashing a beam of stable atomic nuclei into a target, they created a fleeting resonance that looked exactly like a particle composed of 4 neutrons and nothing else. It existed for just a billionth of a second before disintegrating, but its signature was there in the debris. The implications of a confirmed tetraneutron are profound. It would mean that our understanding of the strong force, the very glue that binds atomic nuclei together, is incomplete. The equations we use to describe nuclear interactions would need a fundamental revision to account for how pure neutron matter can bind, even if only for a vanishingly brief moment. This is not just a laboratory curiosity. It is a direct window into the most extreme matter in the universe, the crushing cores of neutron stars. These cosmic remnants are essentially giant atomic nuclei, city-sized spheres where gravity has overcome all other forces, packing a sun's worth of mass into a space the size of a mountain. The interior of a neutron star is a quantum soup of unimaginable density, where the distinction between individual neutrons blurs. Protons and electrons are squeezed together, and matter may exist in exotic forms like a superfluid or a crystal of pure neutrons. The tetraneutron, if real, could be a tiny, fleeting hint of the kinds of neutron clusters that might form in that insane environment. It could be a signpost pointing toward new, stable or semi-stable forms of matter that only exist under pressures we cannot replicate on Earth. The controversy continues as other experiments have failed to reproduce the result. But the possibility alone is a thrilling reminder that the laws we discover in our particle colliders are the same laws that sculpt the most violent objects in the sky. By creating a speck of impossible matter for a fraction of a second, we might be glimpsing the hidden architecture of a neutron star's heart. The fleeting existence of an impossible particle hints at the strange rules governing matter under extreme pressure, but there is a place in the universe where the very laws of physics are thought to break down entirely. This brings us to the final and perhaps most profound cosmic contradiction, a paradox that strikes at the heart of reality. It is the black hole information paradox, a theoretical war between the two greatest pillars of modern physics, quantum mechanics and general relativity. To understand the conflict, we must first accept two foundational truths. Quantum mechanics, the rulebook for the very small, insists that information is never truly lost. If you burn a book, the ashes and smoke seem to erase its story, but in principle, a being with perfect knowledge could reverse the process, gathering every particle and photon to reconstruct the original text. Information, in the quantum sense, is always conserved, it is merely scrambled. General relativity, Einstein's theory of gravity that governs the very large, presents a very different picture of a black hole. It describes a point of infinite density, the singularity shrouded by an event horizon, a one-way membrane in space-time. Anything that crosses this horizon is gone forever, lost to the universe outside. Its information is irretrievably trapped at the singularity. For decades, physicists accepted this grim picture until Stephen Hawking made a startling calculation. He realized that black holes are not perfectly black. Due to weird quantum effects happening just outside the event horizon, they should slowly evaporate, emitting a faint, random hiss of particles now called Hawking radiation. This radiation carries away energy, causing the black hole to shrink and eventually vanish. And here lies the paradox. Hawking radiation, according to his original math, is purely thermal, like the heat from a stove. It contains no information about what fell into the black hole. So, imagine a book falls in. The black hole eventually evaporates, leaving behind only this formless, random heat. The book's information, the specific arrangement of atoms that made its story, is gone, erased from the universe. This violates the sacred quantum law of information conservation. It creates a cosmic crisis. One theory says information must be preserved, the other says it is destroyed. This is not a minor technicality. It is a fundamental clash about how reality works at its deepest level. The search for a solution has led to some of the most mind-bending ideas in theoretical physics. One revolutionary concept is the holographic principle. It suggests that all the information that falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon like a cosmic hologram. The three-dimensional interior, with its crushing singularity, is a projection from this information-rich surface. When the black hole evaporates, this information is slowly and chaotically released in the Hawking radiation, scrambled but not destroyed. Another, more violent proposal is the firewall hypothesis. It argues that to preserve information, the event horizon cannot be the smooth, gentle gateway general relativity describes. Instead, it must be a searing wall of high-energy particles, a literal firewall that incinerates anything trying to cross, destroying the infalling object but preserving its information in the resulting energetic blast. Both ideas, while mathematically intriguing, come with their own profound costs, either abandoning our intuitive picture of space or violating Einstein's principle of equivalence, which says free fall should feel like floating in empty space. The black hole information paradox remains unresolved, a glaring sign that our understanding of gravity and quantum theory is incomplete. It forces us to ask what truly happens at the edge of a black hole, and whether the universe keeps perfect records of every event that has ever occurred within it. This is more than a puzzle about stellar corpses. It is a direct question about the fabric of reality, a final cosmic contradiction waiting for a theory of everything to finally make it add up. From impossible particles to cosmic paradoxes, this journey through 25 discoveries reveals a universe that thrives on contradiction. Each one is a crack in our current understanding, not a flaw in the cosmos, but a signpost pointing toward a deeper truth we have not yet grasped. These are not failures of science, they are its very engine. Every anomaly, every measurement that stubbornly refuses to fit, is an invitation to explore further, to question more deeply, and to dream bigger. They remind us that our most elegant theories are not the final word, but merely the best map we have drawn so far of a territory far wilder than we ever imagined. The universe is not a static museum of facts. It is a living, breathing puzzle, constantly challenging us to expand the boundaries of the possible. So the next time you look up at the night sky, remember you are not just seeing points of light. You are looking at a tapestry of unanswered questions, at the silent dance of dark matter, the relentless push of dark energy, and the faint echoes of events that defy all logic. Let that wonder fuel your curiosity. Which of these 25 cosmic mysteries keeps you up at night? Is it the silent, overwhelming presence of dark matter, the eerie perfection of the odd radio circles, or the existential riddle of the Fermi paradox? Share your thoughts in the comments below and let us know what futuristic frontier we should explore next. If you enjoyed this deep dive into the cosmos, be sure to like this video and subscribe for more journeys to the edge of understanding. The universe is strange, wonderful, and